of closes the whole thermodynamic spectrum, entropy, the second law of thermodynamics, and heat engines and refrigerators. So we talk about this deep concept. I mean, you could literally listen to lectures on entropy for hours and hours and hours and still not understand it. Entropy is like kind of like quantum mechanics. It's one of those things that we know about, we've heard, but you still, it's abstract, very abstract, like quantum mechanics, you know. You're still trying to understand it. What is entropy? Information theory, entropy, the arrow of time, and all of those things have been related to entropy. And then heat engines and refrigerators. Why can't we have 100% efficient heat engines? Why can't we have 100% refrigeration? Well, that comes back to the second law of thermodynamics that says the entropy of the universe always increases over time, right? But then what is entropy? Then you go back to the definition of entropy. So it's like a cycle. Entropy is something that's describing the disorder of the universe, the disorder of the system. It's something also having to do with some probability theory, probability and statistics, you know. So So a good starting ground would be maybe to look up second law of thermodynamics. Then in the second law of thermodynamics, there's different ways of stating the second law of thermodynamics. Then you go to entropy, right? So let's just review for a second back to the first law of thermodynamics. The first law of thermodynamics was what? Q into gas is delta E of gas plus work done by gas. Right. So, how would you describe the first law of thermodynamics to someone without using this equation? What is the essence of the first law of thermodynamics? What is it saying? Okay, that energy is conserved. I think that's a perfect answer. Like that's what essentially this is saying, right? So if you're trying to explain first law of thermodynamics to a six-year-old kid, because they're always going to ask you, right? I've heard about the first law of thermo. What is it? 6-year-old, you're just going to say, you're not going to put all this. You're just going to say energy is conserved. It just transforms from one form to another, and that's it, you know. But as they get older and you get older, you get more into, well, what does it mean that it's conserved? And then you can say, well, energy comes in the form of heat, which is the transfer of energy from a hot object to a cold object. It could come in the form of kinetic energy of molecules, right, which is internal energy. And energy comes by doing work on something, you know. Then you describe that. So when I put heat into something, its energy of motion changes, and it does work on the system. So you can get more into the specifics. But essentially, first law of thermo is saying conservation of energy at its basis, right? And then energy transformation from one form to another. So energy is never lost, but just transformed from one form, to another. Okay, and then what are those forms? You can get specific into heat, kinetic energy of molecules, work, potential energy, kinetic energy, right? Now, what is the second law of thermo saying? So that's what we want to know. Second law of thermo. Okay, so let's look that up. going to say, well, I've also heard about the second law of thermo. What is that? Right? The 6-year-old kid. So you say, you know what, second law of thermo is a little deeper. Wait 2 years until you become 8 years old, then I will explain. Just think about the first law for now. All right, so that's your answer to the 6-year-old. Okay, so the second law of thermo states that the total entropy of an isolated system. In other words, to explain this, they're using this word. But then you have to say, well, then what is this? But they didn't necessarily have to start out with that sentence. They could have explained it differently and then have to employ the word entropy. But it just depends what source you read, how they go about explaining it. So they first explained it by referring to that. So the total entropy of an isolated system can never decrease over time. Okay? So that's one way you can say the second law. Total entropy of an isolated system, that's a key word, isolated system, always increases. The way that they've worded it is can never decrease. Well, that's the same thing as saying it always increases. Well, no, you know what? If it can never decrease, it could stay the same. Right, so we can say always increases or stays the same. The total entropy of a system and its surroundings can remain constant in ideal cases where the system is in thermodynamic equilibrium or is undergoing a fictive reversible process. Fictive means fiction. So it means reversible processes are never completely, even though we say there are reversible processes, but in the real world they never happen, essentially. So in fictive reversible processes, the entropy could stay the same, right? In all processes that occur, including spontaneous processes, the total entropy of the system and its surroundings increases. And the process is irreversible in the thermodynamic sense, right? Because if the entropy increases, you try to come back to that state, that's it. The entropy is going to increase again. So when you do a closed path integral, it's not zero. Back to the idea of conservative forces, right? So if there's, in the real world, any path that you do is actually not reversible because it's only fictive that there's a reversible process. So the increase in entropy accounts for the irreversibility of natural processes and the asymmetry between the future and the past. You see. So for example, if I raise my hand, then lower it, energy is conserved, right? It goes from it goes kinetic to potential, and then if I drop it, it goes back to kinetic. But the process is not reversible because by doing this, what has happened? Some of the molecules have moved and I have aged a tad bit in the process, right? The molecules in my body have disintegrated during that 1 second that it took me to raise it and lift it. So it's still not reversible, right? Because when I come back to the down, I'm not the same age that I was before. You see? So it's not a reversible process. It's a tad bit irreversible. So what has happened during that time? The entropy has increased. So therefore, there's a asymmetry between the future and the past. So now if you run the movie backwards, right? You go like this and like this, and now run it backwards, what is it gonna show? Like this, like this. It's almost like the movie's gonna look like, you cannot tell, in that case you cannot tell that which movie is being run backwards or forwards, because not much changed, right? But because I aged slightly, there is a difference between the future and the past, you see. But now if I did that for 2 years, right? And now run the movie forwards and backwards, can you tell which one is the forwards?
Yes.
Yeah, because if I'm 2 years, I'll have a beard. In a couple of days, I'll already have a beard, and then in 2 years, I'll have a beard. So now you can say the movie is going this way, if you backwards, the beard all of a sudden is going down. You see? The movie run backwards. And if you're watching that, you say, wait a minute, I know that movies, I know that a beard, if you have a beard, it's not just going to disappear by itself. You see? In other words, we already instinctively know which one is the future. Right? In order to shave the beard, you actually have to do something. But in order to grow a beard, you can just stay there and do something, and then the beard will grow, you see. So, what determines the future and the past? The future is always the direction in which entropy is increasing. So, is having a beard a larger entropy than not having a beard?
Yes.
It must be, you see. It's a state of more disorder when you have hair on your body, because now there's more information you have to. So entropy is also connected to the idea of information theory, right? When you have beard, now there's more stuff about you that I don't know. How much hair do you have? What kind of beard is it? So there's more stuff about you that I need to know before I completely draw a picture of you, right? Like when someone's committed a crime, they say, try to draw a picture of the person, right, as best as you can. If they didn't have a beard, it's easier to draw the picture, right? But then, oh, you know what, I think he had a beard. Well, what kind of beard was it? Oh, a rounded beard. I think he might have had a goatee, you know. You have to try to think. So having beard is therefore a higher state of entropy. There's more stuff that you have to remember, right? That's why the future is different than the past, in that the future always will have more information about it that you don't know. And that's entropy, you see. So we can say total entropy of an isolated system always increases, and then you can now explain this further by saying the future is different than the past in that it always contains more unknown information back then. i.e. beard example, right? Beard example. You could put that in anything, you know, use any other example that you want. So future, so you see there, there's an asymmetry between the future and the past. Historically, the second law was an empirical finding that was accepted as an axiom of thermodynamic theory. What does empirical finding mean?
Experimental finding?
Yeah, it's based on experiment. In other words, we kept doing experiments over and over, and we found that something about the system makes it so that it only goes forward in one direction. It's empirical. What does that mean? Now this introduces philosophy, Immanuel Kant, right? That's why physics and philosophy also go in hand. Empirical evidence is information received by means of the senses, particularly by observation and documentation of patterns and behavior through experimentation. You see, that's why experimentation is so important. The term comes from the Greek word for experience, empiria. After Immanuel Kant in philosophy, it is common to call the knowledge gained a posteriori knowledge. Posteriori means past experience. After you've done an experiment over and over, based on that experience, that's a posteriori knowledge. A priori knowledge is what? Is initially you think about something and you say something has to be some way, right? And then you do an experiment to confirm that a priori knowledge. So empirical knowledge is based on a posteriori knowledge. Wow, now I feel like I'm giving a philosophy lecture now. This is Latin stuff. Okay, now let's go back. So statistical mechanics, classical or quantum, explains the microscopic origin of the law. So in other words, empirically, they found out that entropy increases in thermodynamics. Then the field of statistical mechanics grew out of that. And statistical mechanics tried to explain, well, why is this happening? Why is information growing, right? So now let's look at the statistics of this, Classical order explained. The second law has been expressed in so many ways. I added the so. Its first formulation is credited to the French scientist Sadi Carnot, who in 1824 showed that there is an upper limit to the efficiency of conversion of heat in a heat engine. And then second law of thermodynamics, one way to say it is that there's an upper limit of a heat engine. So I see one formulation of the second law is so different than the other formulation. So there's the Carnot principle, the Clausius, the Kelvin, equivalence of the Clausius and the Kelvin, Planck's proposition. There's different ways of looking at the second law. That's why I said, don't explain this to a 6-year-old kid. Okay? Wait till they're 8 years old. Of course, 8 might be too early also. So introduction. Oh, okay, this is an important equation. Delta S is delta Q. So the first law of thermodynamics provides the basic definition of internal energy associated with all thermodynamic systems and states the rule of the conservation of energy. Oh, okay, so we already said that, right? First law of thermo. The second law is concerned with the direction of natural processes. Do you see that? How natural processes flow in their direction. It asserts that a natural process runs only in one sense and is not reversible. For example, heat flows spontaneously from hotter to colder. So if you have a hot beaker inside of a cold beaker, and this is hotter, the heat will flow only this way. Now, if I want the heat to flow the other way, I've got to do some work, and that's a refrigerator. The refrigerator is something that takes the heat in here, puts it back into the hotter thing. So it takes the cold air in the refrigerator, takes heat from that cold air to make it even colder, and then dumps it out to the kitchen, which is already hot, right? So if you want to reverse this, you've got to do some work by compressing the fluid, right, in the refrigerator. You do work, and then you suck out some heat, but the efficiency is not 100, right? So, for example, heat always flows spontaneously from hotter to colder, and never the reverse, unless external work is performed on the system, you see? This explanation of the phenomena was given in terms of entropy. Total entropy can never decrease over time for an isolated system. Because the entropy of an isolated system spontaneously evolves towards thermodynamic equilibrium, the entropy should stay the same or increase. In a fictive reversible process, an infinitesimal increment in the entropy of a system is defined to result from infinitesimal transfer of heat to a closed system, which allows the entry or exit of energy, but not mass transfer. Okay? So in other words, this is the definition of the increase of entropy. When does entropy increase? When a certain amount of infinitesimal heat, dq, so we're going to write that ds is dq, certain amount of heat comes into a system. So you see here, first law of thermo says if heat comes in, it goes into internal energy and work. But the second law is saying if heat comes in, not only does it do internal energy and work, but that heat that comes in increases the entropy, the uncertainty of the system. So it says to a closed system, so divided by the common temperature of the system in equilibrium and the surroundings which supply the heat. So then therefore, delta S is not just equal to dq, but divided by temperature T. Well, that actually tells us what the units of entropy are then. It's joules per Kelvin, right? Let's see if this definition makes sense just on the conceptual level. If you have a gas at 1 Kelvin degrees, and I put in 1 joule of heat in there, how much did the entropy of that gas increase? So it's a very cold gas, like liquid actually it would be solid by that point, right? Solid nitrogen, solid helium gas. Because by the time you cool it down to that temperature, it turns solid, right? So if that gas is now solid, I put 1 joule of heat in there. So now the molecules are gonna start moving faster, right? Is it gonna do much work? No, because the gas is solid, it doesn't expand much. So all the heat that you put in at 1 Kelvin will go into the internal energy, right? So how much will its entropy increase? 1/1, which is just 1 joule per Kelvin. So 1 joule per Kelvin of entropy increase, think about it this way, is like putting 1 joule of heat in a gas that's at 1 Kelvin. And it really doesn't matter the volume of the gas. It could be the size of this room. That's kind of weird that it doesn't depend on the volume. If I put 1 joule of heat in this room and the gas in this room was 1 Kelvin, what would happen to that 1 joule of heat? It would kind of spread out, right? What would happen? The root mean square velocity of the molecules would shift a tad bit, right? So based on what we learned the other day, it would look something like this. If there's a lot of molecules at 1 Kelvin, it looks like this, right? If I put 1 joule of heat, it would shift it. But this is truly more for gases. I don't know if it doesn't really apply that well for solids. That Boltzmann distribution was more for gases. Okay, so then there's a little amount of shift, so there's more uncertainty about what those molecules are doing, right? So the entropy increases by 1 joule per Kelvin. Now, if I put 1 joule of heat, let's say the temperature of the solid is now 10 Kelvin. Now I put 1 joule of heat in there. Now how much does the entropy increase? 1 joule of heat, but the temperature is already hotter. So 0.1 joule per Kelvin. So if I keep putting 1 joule of heat, and then it's starting to go over, right? So what's gonna happen? The change in entropy is gonna decrease if I keep putting the same amount of heat. Well, why is that? Shouldn't the same amount of heat put into this thing increase the uncertainty the same amount? Well, apparently not. If you divide it by T, it means it depends on the temperature. So if I make it 100 Kelvin, by this point the gas has probably turned into a liquid, right? So now if I put 1 joule of heat, its entropy increases by 0.01 joule per Kelvin, right? Then if I make it 1,000 Kelvin, now the gas is most likely, it turns liquid, and by now it's probably, when do the gases, yeah, by this point it's basically a gas already, yeah. Helium or anything of those gases, because this is already hotter than room temperature, right? So then by this point, it goes 0.001. The entropy increases by less amount. So why is that, do you think? What's happening here? We can explain it graphically, but we can also explain just conceptually.
Right, so it's similar to chemistry, like when you take two solids and when you heat it up, like when you put heat in the system, like the solid's gonna turn probably to liquids or to gases. I mean, in these cases, so the change in uncertainty like increases a lot. But if it's like gases, between two gases or two liquids, so it doesn't really notice the change.
Why?
Like the molecules stays in the same volume, and I don't know like how to explain it, but think about that. Like if it's a solid, you're selling, you just like heat it up and it turns, into gases. So that's a huge change in entropy, but not for two solid. Not
Okay, in other words, look, if I have a 1 kilogram of ice at -5 Celsius,
Yeah.
I put 1 joule of heat in there, what's gonna happen? Then I have 1 kilogram of water at 20 degrees Celsius. I put 1 joule of heat in there. Then I have 1 kilogram of steam. 1 kilogram of steam at 110 Celsius. And I put 1 joule of heat in there. Do you see? We could also give the example that way. Say, okay, what's going to happen to all these three systems, and then how much is the change in entropy of all of them? Right? So what we're saying is that the change in entropy of this is a lot less
Yeah.
versus this versus this.
So
Okay?
because in a low temperature, all properties stays very stable compared to the high temperature. So that means when you put it into the same amount of heat into two different states, low temperature versus high temperature, the low temperature matter is gonna, the change in entropy is gonna be higher than the.
Yeah, but you're restating it.
Yeah, I restated
You're going
it.
back, you're saying liquid is hotter, and so therefore it's liquid, and so therefore 1 joule of heat will cause a higher entropy. Actually, it's the opposite of what you're saying. It's lower entropy.
Okay, so
This is lower.
I would say,
But again, you're just restating the question in your answer.
what I would say is because if you're putting a certain amount of energy into let's say a state that's like a gas that already has I would say huge entropy compared to a solid where the molecules are not moving and they're being in a more excited state, the entropy should be higher because they're in a very what was the word you said? You said that it was stable. It's very
So
stable.
you mean the solid has a lower entropy?
Yes,
Yeah.
the solid.
That I agree. The total entropy you're saying, S total, is lower here. So let's just say it's 100 joules per Kelvin. And then here, the entropy, are you saying the water?
Yeah, let's say that there's a initial entropy, right?
So is this gonna be a higher entropy than that?
Yeah,
Okay, let's say 150. Why? Why does water have more entropy?
The way I would think about it is just that because molecules are so compact, they're kind of staying in the same position. Water, not so much, so they're actually moving around, more entropy.
More information, more, yeah.
And then gas, even more so.
Okay, yeah, exactly. So I agree with that. Let's say 200 joules per Kelvin. But then why is it that if I put 1 joule of heat in here, this one doesn't go from let's say 200 to 201. This should go from 150 to 151. This should go from 100 to 101, right? But it's not going to happen. If I put 1 joule here, this might go from 100 to 101. This might go from 150 to 150.2. This one might go from 200 to 200.01. You see? So that 1 joule affects this guy less than this guy. That's what we're saying,
Yeah.
right? Yeah.
Is it maybe because in solids particles are more compacted, so when heat is applied, they're able to interact a lot
Okay. Yeah.
easier than in a gas where particles are spread out? So it's if that makes sense. I don't know.
Yeah.
But-
That's one way to put it. We're trying to find maybe different ways to put that in, This one already is going slower. But the other way to say it is kind of maybe look at here and say, oh, okay, solid, when you put in heat, it doesn't expand much. Yeah, it does, but not that much. So most of the heat you put in goes into change in temperature. Okay, when the temperature is